Today we're looking at proportional, integral, and derivative. We're looking at the cumulative of all that we've done thus far. We've done proportional integral, proportional derivative. We've done a little proportional integral and derivative together. But today we're going to be looking at how a sinusoidal waveform and a square waveform are going to affect our PID control. So we're going to have this as our process variable, the black line. The red line will be our output of our controller. We have a set point of 50, a bias of 40, integral or proportional gain of 1, integral of 0.5, and derivative of 0.2. Our equation, which seems quite long, but yet we've simplified it because we know that we have different sections to this. We have our bias. We have proportional times air times the direction. Direction in forward bias is 1. In reverse bias is -1. We have our integral. Proportional over integral times your error times your time times your direction. And then we have the cumulative integral of time that has passed by already. And we have our proportional gain. We have our derivative, which is proportional gain times derivative times your delta error over your delta time times your direction. So let's jump right in with this. And I do realize this takes a little bit of time. So let's go through it. And everybody really needs to understand this, okay? So make sure that if you have a problem at any spot here, pause the video and see where these numbers are coming from so that it makes it easy. Because we're not here to complicate, we're here to make it easy. So if we look at our graph here, we're going to look at different points along this. We can't just, we're not just going to calculate this all at one step. We want to know where every spot is going to be and how it's going to affect. So if I zoom in on this, now I really want to zoom in because this is going to get pretty tight pretty fast. We want to see where it is right here, 0.1. 0.2 is going to be right here before it's still on the ramp before it hits the flat. 0.3 is as soon as it hits the flat. 0.4 is before it's still on the flat, but it's just ending that time, heading towards the ramp. 0.5 as soon as it starts the ramp. 0.6 right at the tip of that. That's supposed to be at 50% right there. So that's supposed to be right at the 50% mark. 0.7 will be at this ramp right before it comes to the flat. 0.8 will be on the flat. 9 at the end of the flat. 10 at the ramp. Then we're going to be looking at 11, which will be right there. Now here's where things start to change. When we look at this square wave right here, we're really going to see how derivative comes into effect with a square wave or a very high ramp. We're going to be looking at as soon as it starts the ramp, and then we're going to be looking at when it comes near the end of the ramp. We're going to be looking at what happens when it hits the top of the ramp and starts to go on the flat, and then same thing here, when it just ends the flat and starts to come down. Then we're going to look at when it goes on this ramp, when it goes on the flat, when it comes to the end of the flat, when it comes to that ramp, and finally ending with our endpoint. Okay, so we have 20 different points that we are going to hit along this line. So we're going to come over, we're going to look at number 1. As soon as it is coming along, its error is 0 currently. And we know if the error is 0, proportional is not going to do anything. Integral is not going to do anything. But as soon as it starts to go on this ramp right here, derivative is going to start to do something. So we're going to go V out equals, our bias is 40 plus proportional gain of 1 times 0 error at this point times our direction, which is -1. Plus, now this is our proportional. Now we look at our integral, which is 1 over 0.5 times an error of 0 times a time of 0 times a direction of -1 plus 0 accumulative integral, because we haven't gone anywhere yet, so we're still at 0. But now here's the part that I need to a little smaller. Now, derivative is the part that is going to do something. So we add proportional gain, which is 1 times 0.2 times our error, which over the course of those 10 seconds is going to be an error of 10%. So we're going to go 10% over 10 seconds in minutes, which is 0.166. Now, to make the math easy, I did this in a square, more of a square wave, right? I did a rectangle. So because I did a rectangle here, we don't have to get into complicated math. We know that the area of this is going to be 1/2 of 10, right? It's not 10, an error of 10 the whole way. It's 10 divided by 2, right? If we do a triangle, it's 10 divided by 2. So we have an error of 10. So it's an error of 10 divided by 2 divided by 0.06 times the direction, which is -1. So our V out equals 40 plus 1 times 0 times -1, which is 0, plus 1 over 0.5 times 0 times 0 times -1 is 0, plus our cumulative integral, which is 0, plus 1 times 0.2 times 10 divided by 2 divided by 0.166 times -1, which gives us 12 negative. That would be a negative 12.046, which equals, that should be 27.952. So now we look at our graph here, and we're going to go to 10, 27, and we're going to come down to here. Okay. Now, at point 2, what is going to happen? At point 2, sorry. That was not supposed to go down over time. That derivative is instantaneous. So it's going to come down to 27 instantaneous. It's going to have that drop, right? As soon as it started that ramp rate, because derivative goes based off of ramp rate, as soon as that point number 1 there. You see I didn't put that right there? I didn't put it right here. I put it right here. As soon as it started the ramp rate. Not right at the instantaneous, but almost instantaneous. As soon as it starts that ramp rate and the controller has time to calculate, it says, oh, you're supposed to be down here because of derivative. Not because there's no integral that has taken place. The proportional still hasn't done anything because it hasn't really deviated from its set point. But the derivative, it sees a ramp rate, and so it drops our output by 12.046. Or, yeah, 12.046. Okay, so now we're looking at point number 2. And I am sorry, that was... I got a little ahead of myself there. That was for integral. That was for integral when we do that calculation. When we do derivative, we're not looking at over time. We're looking at ramp rate. That was my mistake. Sorry. I will clear that up right now. Now we are looking at integral. I hate when that does that. 40, which is our bias, plus. Now we have, if we look at our, where we are, our point number 2, we have an error of 10, right? So now proportional matters. Now we have 1 times our 10 of an error, so proportional gain times error of 10 times direction of -1, plus our integral of proportional over integral times our time, which is 0.166, which is 10 seconds in minutes, times our error, which is 10 divided by 2, because that is the triangle, right? When I looked at this triangle right here, and I was doing that on derivative, I was supposed to be doing that on integral. Integral. When we calculate, if we were to calculate out this integral box right here, that would be an error of 10 the entire time over 10 seconds. This one here is an error of 5 over the entire time, right? Because it's 10 divided by 2 because it's a triangle. Okay? So 10 divided by 2. Plus our ongoing accumulative integral, which is still 0, plus our derivative, which is still on that ramp. So 1 times 0.2 times 10 over 0.166 times direction of -1, which gives us 40 plus. Now we have 1 times 10 times -1, which is minus 10 plus 1 over 0.5 times 0.166 times 10 over 2, which gives us, oh, and we were supposed to times that by our direction, which gives us negative 0.166 plus our accumulative integral, which is still 0, plus our derivative, which is negative 12.046. When you add all those up, it should be 16.29. So now we come back to our graph. And we're going to go down to 16.29. Now this may not have been the best, most linear drawing I've ever done, but that's where that one goes up. It's right there. So now at point 3, now the derivative has stopped because now the ramp has stopped. So now we're on the flat plane as soon as we get to 3. So now the derivative is not going to have a ramp rate. We can all see that, right? When we come to here, when we're at position number 2, we were at almost 10, an error of 10 plus 10, but we're still on the ramp. But when we get to 3, we're on the flat. And so it does not have a ramp rate anymore. So let's look at that now. So now, that was 1, 2, and 3. V out equals. We always have the bias, so we just always have to rate it. 40 plus 1 times 10 times minus 1, that's our proportional. We have an error of 10 still, plus an integral of 1 over 0.5 times. Now, the difference in time between point 2 and point 3, not an actual decimal point, the position number 2 and position number 3, there was no time. Okay, it was like 0.01 seconds. So for our application here, we're going to call the time is 0. Even though there's still an error of 10 times the direction of minus 1, plus our cumulative integral, which we look up here, is negative 0.16 times our derivative of 1 proportional times derivative. Sorry, that was supposed to be plus. That was supposed to be a plus our derivative of 1, our proportional, times our derivative, times our error, which our error is 0 over the next 10 seconds, times the direction of minus 1. So we have 40, our bias, plus our proportional of minus 10, plus our integral of 0, plus our cumulative integral of minus 0.166, plus our derivative of 0, which equals...
Actually, how do we get the accumulated integral there?
Okay, 1 second. Which equals 28.34. 28.34. So, notice our derivative, just like before, just like in other theory, in other lab, our derivative takes control and it comes down, and as soon as the ramp rate stops, it comes back up, but not all the way up to where it was before because of proportional and integral. Now, where did we get that accumulative integral from? How much integral did we get from this space right there? How much integral did we get from there?
0.166.
A negative 0.166, right? Because this is reverse acting, right? So anything that is above that line, we're going to be going in the opposite direction, right? So we got an integral of negative 0.166 from that spot there. Now that is going to accumulate, right? That's not going to go away because integral is over time. Now I say it's not going to go away, but we're going to see what's going to happen, right? That's a little foreshadowing if you want to talk English. Okay, so now we're looking at so that was 0.3. So now we're traveling along the plane of the top.
Should be like integral be 1.66, not 0.166. I was just looking over.
Yes, thank you. That was supposed to be 1. Sorry, I'm doing some of this stuff off of memory, and I'm not even checking my notes, and I'm not using a calculator. So that was supposed to be negative 1.66, negative 1.66. Thank you. The answers are still right. Okay. So at position 4, we've gone along the plane. So V out equals 40, our bias, plus we are still at a 10 error, a positive 10 error, times the direction of minus 1, plus 1 over 0.5. Now, how long have we been on this plane for? We've been on it for 10 seconds. So we have, so we go our error, so we times that by our error of 10, and we times that by our time, which is 0.166, times our direction of minus 1, plus our accumulative of negative 1.66, plus our derivative of 1 times 0.2 times 0, sorry, it is a 0 error over 10 seconds times your direction. So we see this starts getting repetitive, but you're going to see that the numbers keep on changing. So we have 40 plus, we still have negative 10 plus. Now our new integral is going to give us negative 3.32 plus minus 1.66. That's our cumulative integral. That's our new integral. Plus our derivative of, because we have 0 error over that amount of time, is 0. Which equals, what is this, 4? 25.02. What does that mean? Really what that means is that this integral right here, we now accumulated another negative 3.32, and sorry, that was supposed to be a 166. So we accumulated another 3.32 worth of integral output, right? So now, over that length of time, from 3 to 4, we went down to 25. So we went down to 25. So now at 0.5, we start the ramp rate again. But the ramp rate is going down. Now, keep in mind, if this was a waveform that looked like this, this is kind of the output you'd expect to receive. Okay, it's not going to be identical because on a flow system or on a level system, obviously it's not going to be a square, a perfectly straight line, a perfectly ramp rate, but it's going to be very similar to what you're seeing here. So now at 0.5, we start our ramp rate again. 40 plus, that's our bias, plus our proportional gain times our error still of 10 times our direction minus 1 plus our integral 1 over 0.5 times. We still have an error of 10, but our time is 0 plus our cumulative integral. So we have to go 3.32 plus the 1.66, which gives us 4.98 negative 4.98 plus our derivative, which is 1 times 0.2 times 10. That is a minus 10 over 0.166, which is our time, times minus 1 our direction. That's a minus 10 because we are going, remember, we look at this here, our error goes from 60 to 50, right? Before, now we're talking about ramp rate, okay? We're not talking about the difference between our set point and our process variable. We're talking about the ramp rate. So in order to get the ramp rate, we went from here to there over 10 seconds, right? And we didn't go in a positive direction, we went in a negative direction. So we went negative 10 in 10 seconds, negative 10% in 10 seconds. On this one, we went positive 10% in 10 seconds. So now that we're going negative 10% in 10 seconds, we put a negative 10 over 10 seconds. That makes sense, right? So now, that equals our bias of 40 plus our proportional of minus 10 plus our integral, which has a 0 time from 0.4 to 0.5. There was no time there. So we have 0 plus our cumulative integral, which is minus 4.98 plus our derivative, which is a positive 12.048, which equals 37.05. Now, you're going to notice a little bit of a trend here. So, 37.5. It jumps up to 37, about there. So as soon as we started to come on this ramp rate coming down, we jumped in a positive direction because derivative does not like change. When there is change, derivative is trying to compensate so that there is no change. Now, obviously, we want change in controllers, but the purpose of derivative is so that you don't overshoot. You don't get too much of a ramp rate. It wants to slow down that ramp rate. It wants to slow down the change. So we have, if we looked at it like this as well, that is 1, 2, 3, 4, and 5. You can match these up with these numbers there. You can match the positions up together. Okay? So now, at position 6, we are still going on a same ramp rate, going from 5 to 6 as we are 5 to 7. However, you do need to stop at the set point because that is going to change the direction of the integral, which is going to be calculated. Normally, if the set point was up here, you could just, if that ramp rate was all the same, you could just carry on your calculation. Excuse me. You could carry on your calculation right from 5 to 7 and not even stop at 6. But because you are changing direction, we're going to need to know the integral here, and we're going to need to know the integral here. And those will be two different integrals, right? Obviously, one's going to be positive and one's going to be negative. So the first thing we're going to do is we're going to calculate out 6 at position 6, right at the set point of 50. So obviously, our error is now going to be 0. So, at position 6, V out equals our bias of 40 plus our proportional gain of 1 times an error of 0 times -1 plus our integral of 1 over 0.5 times 10 divided by 2 times 0.166. Now, why did that happen? I said that the error was 0. But remember, when we're doing integral, integral is over time. So again, we still have to calculate out this amount of integral. How do we calculate out that amount of integral, Nikita? It's within, so good question, but no. What happens is our error is 10. It's over 10 seconds. So it is 10 divided by 2 over the 10 seconds. So we still have, it is, if you were to spread this out like this, it would be an error of 5 over the 10 seconds, right? So it's 10 divided by 2, which gives us 5. Okay, so that gives us the 10 divided by 2 times our time times our direction plus our cumulative integral of -4.98 plus our derivative of 1 times 0.2 times -10 over 0.166 times -1. -10 because we're still going in the negative direction. Okay, so that equals 40 plus plus 0, because we're at 50. Our proportional has an error of 0. It is 0. Plus our new integral of, that is 1.66 plus our, that is a -1.66 plus our cumulative integral of -4.98 plus our, because we have two negatives, it is 12.048 of derivative. When we add all those up, we should get 45.42. So now, we're going to get 45.42. That's at 0.6. So now we're going to carry on, and we're going to end up at 0.7. And you're going to see there's going to be, it's going to look like it goes straight, that this line goes straight, but it does not go perfectly straight. And we're going to see something very interesting here, which we have never seen before. Because we like to keep things interesting and to keep doing things that we've never done before. So V out equals 40 plus our proportional of 1 times negative 10, because we are now at, we still have a set point of 50. Our process variable is at 40. So we have a negative 10 error times our direction of negative 1 plus our integral of 1 over 0.5 times an error of negative 10 over 2 times our time of 0.166 times negative 1. We're going to add our old integral, which is 6, what is it? What are we on? 7? 6.64, and that is a negative 6.64 plus our derivative of 1 times 0.2 times minus 10, we're still going in the negative direction, over 10 seconds times our direction. And that is going to equal 40 plus, we have a positive 10 plus, we have an integral of 1. So now we're in the positives, 1.66 plus negative 6.64 plus 12.048, which equals 57.048. Okay. So you notice that we went from 37 to 45 to 57. Okay? That is not linear. Notice that here we have our integral is positive, or sorry, our proportional is positive, our integral is positive, but because of our cumulative integral, which has happened in time past, we still end up with a minus 5 integral. So the integral is still trying to drop us down because of what has happened in the past, right? But our proportional doesn't care about the past. Our proportional just says, at this time, you have an error of minus 10, so I want you to go positive, right? But our integral says, I want you to go positive too, but because of our past experience, everybody goes based on their past experience, right? Based on our past experience, you've always had a positive error, so we're going to keep a negative error on there. And our derivative says, and you're still ramping negative, so I'm going to give you a positive output. Okay, so we've got 57. And so, like the question was before about our cumulative integral. Do you see how that integral is accumulating? Do we see that? That all that time that was spent with an error, a positive error, that has been accumulating a negative integral output. But now we're finally getting to a time where we're saying, well, now I have some negative time under my belt. So now I'm going to give positive integral. And when I add these up, I'm still negative 5, right? Negative 4.98. So now at 0.7, we came up to 57. So right about there. So that was 0.7. We came up to almost 60, 57.048. So now at point number 8. At point number 8, we have now stopped the negative trend, the negative slope, and now we've plateaued. Well, that is going to affect our derivative. It is not going to affect the integral because between points 7 and 8, there's no time. Okay? So we still have all this past integral to take into account, but we won't have any new integral to take into account. So let's do this. We have position number 8. V out equals, we still have the bias of 40 plus 1 times, we have an error of minus 10 still, times direction of minus 1 plus proportional over integral times, we have an error of minus 10, but we have 0 time times our direction, plus our cumulative integral, which is 5, well, it's 4.98. And it's a negative 4.98. When we add 1.66 to a minus 6.64, plus our derivative of 1 times 0.2 times 0 error over the next 10 seconds. So our ramp rate will be 0 times minus 1. And that equals 40 plus 10 plus 0 new integral plus minus 4.98 of old integral plus 0 derivative, because we have plateaued. And that now gives us 45.02. So now, instantaneously, we've dropped down to 45. Okay? Let me zoom in a bit here. We have dropped down to 45. That was 0.8. I'm going to erase that line, and I'm going to replace it with a highlighter. Because I don't want to get the next line confused, okay? That's just to eliminate confusion. Okay, so now at point 9, what would we expect to see and not to see? We would not expect to see any derivative action, right? Because there is no ramp rate. We are plateaued. So we would not expect to see any ramp rate. We would expect to see proportional output, right? Because we're not at our set point. We would expect to see new integral because we have a time period in which we have to calculate out all of this area right here. We would expect to see our old integral because we still have all that data from time past. So we expect to see proportional, new integral, old integral, no derivative, and still our bias. So when we break it down with those 5 things like that all the time, it makes it fairly simple. So at number 9, V out equals 40 plus our integral times our direction plus our proportional over our integral times our time of negative 10 times, sorry, did I say time? That was our error of minus 10 times our time of 0.166 minutes times our direction plus our old integral of minus 4.98 plus our derivative of 1 times 0.2 times a ramp rate, an error of 0 over 0.166 minutes times the direction. That now gives us 40 plus 10 plus, that would be 3.32 plus minus 4.98 plus 0, which would give us 48.34. So now, over the next 10 seconds, we go up to, I'm going to zoom in on this because I need to get close. Because we haven't went up a lot. We went from 45 up to 48 because of the integral action that occurs at this point. Now, all of a sudden, we hit a new ramp rate. Where would we expect to see our signal go? Our output signal. Where would we expect to see it go? Well, we would expect it, because it is going, our process variable is going up, we would expect our derivative to drive down, to try to stop this ramp from happening. So that's just something to keep in our minds. Where would you expect it to go? Not just what do the numbers say, what would you expect from it? So now, as from 9 to 10, there is no time difference that have happened. It's just now all of a sudden we started ramping. So there's no time. We still have our proportional. We still have, now we have derivative, and we have all of that past experience. And now that integral added 3.32 to our integral. And you see how if we keep adding these, we take this and we go, okay, well, that one cancels out that one, and that one cancels out that one. So now we have an accumulative 1.66 of integral, right? Because they cancel each other out after so much time has gone on. So now we are at point 10. We're going to get to point 11, and then we're going to take a little break. 10. V out equals 40 plus 1 times minus 10 times minus 1 plus our integral, our new integral of 0.15 times minus 10 with a time of 0 times direction of minus 1 plus our old integral of negative 1.66. We add those together. Plus our derivative of 1 times 0.2 times, we have an error of 10% over the next 10 seconds, times direction of minus 1, which equals our bias plus 10 of proportional plus 0 of new integral plus negative 1.66 of the accumulative integral plus a minus 12.048 of derivative, which when all said and done gives us 36.32. So now, we will end up at 36.32. Now that was point 10, and that was 9, right there. Well, now we're going to have to calculate out all the integral of here, right? Because now we know that derivative shot us down. We know that as we come along here, we're going to be coming up in the upward direction because that's where integral wants to drive us. But also, integral wants to take us, it wants to increase the output because this is negative, right? But what's going to happen with the proportional? We're going to go from a proportional of, we have a minus 10 to an error of 0. So our proportional will disappear. So let's do this. We're going to go to position 11. V out equals 40 plus our proportional, which has an error of 0 at this point, times -1 plus our integral of 1 over 0.5 times, it is negative, and it's 10 divided by 2 because it is half of, it is a triangle, and it's half of the area of the 10, times the time, which is 0.166, times the direction, plus your old integral, which is minus 1.66, times your derivative, which is 1 times 0.2, times 10 over 0.166 times minus 1 the direction. And that gives us 40 plus 0 plus, we will have a positive 1.66 plus a negative 1.66. That is the cumulative integral and the new integral. Plus, we still have minus 12.048, which equals 27.952. Now you notice the old integral and the new integral now make 0, right? Why is that? Because they canceled each other out, because the time that we spent, all of the error that we had, positive error, all the positive error that we had the exact same negative error for the exact same time, so it would make sense that over time, it cancels completely out because it is error over time times your proportional. Well, we've had the same amount of time with the same amount of error, so if they cancel out, that means it makes 0. So our proportional is now, our running total of proportional now is going to be 0 because that equaled 1.66, and so that canceled out that final one. So now we have 20, what do we have? 27. So we drop to 27. Let me see, where are we here? 10. So we actually still increased. Is that correct? That is not correct. What happened here? 10 was supposed to be 36. 36, okay. So 20, I'm going to get rid of this as well. Okay, that was kind of in the way. So 27 would be about here. So it decreased. Okay, so that is 0.11. We're going to take a break, and then we're going to come back, and we're going to see what a square wave does to derivative and 2 integral, and 2 proportional. Okay, we're going to start back into this thing. We're going to finish it off. So we have essentially looked at what would happen to a controller output when the process variable goes above the set point and then below the set point, not in a digital or square wave format, but it has a bit of a ramp. Now, notice that the output did not just follow the reverse action of the process variable, but yet it almost looks like there's spikes. Okay, that's because of the derivative function that was happening. Okay, now we're going to look at what happens if there's a big step change, like somebody just opened up a valve and it dumped a bunch of water and then they closed the valve. Okay, let's see what would happen. And now this is instantaneous, mind you, but let's just see what would happen if it was instantaneous. Okay, so at point 12, now point 12, and I want to recognize this, that point 12, or position 12, whatever you want to call it, is right there, okay? Where this ramp stopped and this ramp has not started yet, okay? We're going to take, like, this is like the tiniest snapshot that you could ever imagine, okay? Every other one has always been either right here or right there. We've never actually looked at one right in the middle. But this is because this is finishing off that sinusoidal waveform. So I want to look at what happens right at that last little spot. Okay? Now, if we don't have derivative, and our integral has all canceled each other out, and the error is 0, I mean, let's think through that in our minds, what it should be without even doing the math. If there's no ramp rate, that means there's 0 derivative. If there's no error from your set point, that means there's going to be no proportional output. If the integral has already canceled all of itself out, there's no existing, no accumulative integral, and the time between point 11 and point 12, there's 0 time. So there's no new integral.
It's just back to bias.
So we're back to bias. So I'm not even really going to calculate that one out, okay? We're going to skip that one altogether because we can logically determine it, which went right back to his bias. So isn't that nice? I actually meant to finish that one off before we took a break, but it goes right back to our original 40%, which would be right about there. Let's call it there. Okay? So that is point 12. Now, I'm going to have to get fancy with some colors because we're going to have something happen here. Okay. We have point 12, point 13, and point 14. So, this is instantaneous, okay? This comes up here and all of a sudden it changes. So let's see what happens. We're going to look at 13 now. So just so we don't have a blank spot here, we're going to go 12 V out equals our bias plus no proportional, no new integral, no old integral, no derivative, which equals 40. Okay? 13. So now we've all of a sudden had a spike, right? Because we're looking at that square wave. So now we have the spike, and it's going straight up. So now we have our bias. Still does not go away. we have our proportional of 1 times, we have an error of 10 times minus 1, our direction, plus, we have no time on the integral. Okay, so I'm not even going to write that out. 0. We have no new integral. 0. But we do have derivative. Okay? We have proportional times derivative times our error. And our error is 10. It's going in the upward direction. But our time is almost 0. Right? It's not 0, but it's almost 0. It's like it's going instantaneously up. And so let's call our time 0.01 times our direction. So we have a bias of 40 plus our proportional, which is going to be negative 10. No new integral, no old integral, plus now our derivative. 1 times 0.2 times 10 over 0.01. Well, that's 100% right there, right? That's not 100%. That is 1,000%, right? 1,000%. So this number really would be negative infinity. Okay? Really is what that number really means. I know that I put 0.01, but it's like 0.001. Okay? It's just so much that it doesn't even matter. Because now that means that our output is what? Our output of our controller minus 3.3. Right? Minus 3.3, not because that's what the math says. The math says it should be just through the floor. But the fact is our output from our controller can only go to minus 3.3. And so, we come back to our graph here. And it is going to drop to negative 3.3. Okay? But then, as soon as the ramp rate ends, so now we're looking at 14. So we went from right here to right here. Okay? We went from right there to right there. The time is so little difference, but now there's no ramp rate. So this great big spike down, we're not going to have that now, but we did get the spike. There's no doubt about that. We got the spike. Okay? So now, scrolling. Okay, so 14. So now we have plateaued. We still have our bias. That's my adding sign. Okay. Come on. 40 plus 1 times our proportional times our error times minus 1. Plus our integral, our time is still 0. So I'm not even going to do integral. And we still don't have any old integral, so it's still 0. Plus our derivative. Well, our derivative is 1 times 0.2 times, now we have an error of 0 over 0.166 times the direction of minus 1, which is reverse acting. That now equals 40 plus minus 10 plus, and that all equals 0 because there's 0 error. So, sorry, 0 new integral, 0 old integral, and 0 derivative, which equals 30. I got that right. 30, right on. So, now, at point 14, we come back up. Now, point 11 was, I think, 27. 27. So we come all the way back up to where we just were pretty well. Right there to point 30. I'm going to put a different color here just to show that it comes back up to point 30. And that is our, now let me see here. We're going to be going in that direction. So that is our 14. 14. So if the controller was fast enough, okay, if it was fast enough, which it's not, but you would see it go, it would come down here, it would jump up, spike down, come right back up. So in reality, what you would expect to see from a controller, even though this is the true math, what you would expect to see is it would come to this point, to 27.7, and then all of a sudden you'd see it kind of go like this. But it would come right back to 30 so fast that all you would see is the numbers just kind of go like this for a second. Right? Does that make sense? It's not going to come up and go down and then come up because it needs a second to read that ramp time anyways. Okay? If you noticed in the labs, when we saw how the controller responded, it wasn't instantaneous. When we all of a sudden had an input ramp rate, our output wasn't instantaneous of derivative, right? It kind of came down slowly, and then the derivative worked. That's because the derivative needs time to analyze that ramp rate. Even though it can do it very quickly, it still needs time. And we're saying that this is an instantaneous spike up. So in reality, it would just kind of do a little jog here, and it would be at 30. Does that make sense? Okay, so that's point 14. Point 15, we're going to be looking at this section here again. We can see that we're going to be calculating for integral. We can see that there's an error, so we're going to have proportional. We can see that there is no ramp rate, so there's going to be no derivative. And we know that at this point we had no existing accumulated integral because it all canceled each other out. So we have no accumulative integral. So we have our bias, our proportional, our new integral. No old integral and no derivative. So when we go to our calculations. Now, the reason why I keep harping on that is because if you say it like that in your head, and then you do the math and you go, where am I getting this derivative from? Or where am I getting this old integral from? It triggers that in your mind to say, no, I should not have that. Okay, so 15. V out equals our bias plus 1 times 10 times minus 1 plus our new integral of 1 over 0.5 times 10 times error of 10 times a time of 0.166, 10 seconds, times negative 1 direction plus 0 old integral plus, and we have no derivative because we have no ramp rate, 1 times 0.2 times, we have an error of 10, sorry, an error of 0 over 0.166 seconds, or minutes, times negative 1, which equals 40 plus minus 10 plus That gives us minus 3.32 plus 0 plus 0, which equals 26. What are we? 26.68. Okay. So now we're going from 30 down to 26.68. That is 15. Well, now you can see we have an instantaneous spike down. Okay? Now we knew what happened on the instantaneous spike up, right? So we know exactly what's going to happen here. We don't even have to do the math, but we're going to anyway, because we like math. Okay. So we're going to do 16. V out equals 40 plus. Now, we're going to go 1 times minus 10 times minus 1. Notice I didn't stop at the set point. Okay? I'm going right through the set point. Whereas when we did it before, and I said you need to stop at the set point, right? Do we remember why we stopped at the set point before? Because there was integral involved. This time you can stop at the set point if you want, but you don't need to. You can go right past the set point because there's no integral involved. We already know that there's no integral involved, right? Because there's no time involved. So we go 40 times our proportional plus our integral, which is 1 over 0.5 times negative 10 times 0 time times our direction, plus our old integral of minus 3.32 times our derivative of 1 times 0.2 times, we're going in the negative direction, and it's actually negative 20 is how far we went, not negative 10, right? We went negative 20 over 0.001 seconds times minus 1. So we have a bias of 40 plus our integral of 10 plus our, so did I say integral? Proportional of 10 plus our integral of 0 plus our old integral, or accumulated integral, of minus 3.32 times our derivative. Yep. Excuse me. Now you can see that we have 20 over 0.001. So it's going to be, I don't know why that's a time sign. That's supposed to be plus. Plus infinity, which gives us an output of 103.3, because that is the max our output our controller can output. So now at point 16, you're going to see that we spike all the way up to 103.3, and that is point 16. Well, now at point 17, we hit the plateau where there is no ramp rate anymore. So 17. V out equals 40 plus 1 times minus 10 times minus 1 plus our integral. We still have 0 time, so our time is 0, plus our old integral of minus 3.32 plus, now our derivative is going to be 1 times 0.2 times an error of 0 over the next 0.166 minutes times -1. So we have 40 plus 10 plus 0 of new integral plus -3 of accumulated integral plus 0, which equals 46.68. So now we're going to come all the way back down to 46. We're going to come all the way back down to 46. I'm just going to go in the opposite direction just to make it easier on myself. But it comes to 46 right here. So that is 0.17. So again, we spiked up and came back down. Now again, that is the theory, but in practical, the controller, you're going to see it spike, and it might go past, it might go up to 60%, it might go up to 70%. I don't know. But what I do know is if it could, it would jump all the way up to 103.3. So now we're at 46.68, and we're almost done here because that was 0.17. The ramp rate has stopped, so now it has leveled out. Now we have to calculate out the integral for this section, right? Now, without even calculating it, we already know that this one had minus 3.32. That's exactly the same, but in the opposite direction. So just out of common sense, you're going to say, I know that's going to be 3.32, right? And there's going to be no derivative. The new integral is going to cancel out the old integral. So there's going to be no derivative. There's going to be no integral because they cancel out each other. And there's going to be proportional and bias only. So you could honestly just look at that and just say, even after all this math that we've been through, we'll have to calculate out the proportional and the bias. It's as easy as that. But we're going to calculate that with them anyway just to prove the point. Whew. We're getting down there. Okay. So, at point 18, V out equals our bias plus our proportional gain times -10 plus, times -1, right? What are we at, 18? Starting to lose my mind here. Plus our new integral of 1 over 0.5 times -10 times 0.16 minutes times -1 direction plus our old integral of -3.32 plus our derivative of 1 times 0.2 times 0 error over the 1.66 minutes times the direction. So our output equals bias of 40 plus proportional output of 10 plus an integral, a new integral output of 3.32 plus an old integral output, an accumulated integral output of 3.32 negative, plus no derivative. And you can see that these cancel each other out. Minus and positive, which equals 50%. Okay.
They're going to be able to find it soon.
Holy moly. It's it is nice being able to zoom in with this detail though. Okay, so now we were at 46, but now we're coming up to 50% at point 18. Okay, 18. So now we have to just simply do 19 and 20, and we are done. So at position 19, V out equals 40. You'll never guess that. 40 plus. Now our proportional. We have went back up to the set point, right? So now our PV has went back up to the set point. So we have an error of 0 times the direction of -1 plus. Now, this was instantaneous, so we have 0 integral. We have 0 old integral. Those canceled each other out. Plus our derivative of 1 times 0.2 times 10. So it went up 10, right, positive 10, over 0.001 seconds times -1, because this was an instantaneous jump again. So now it's going to go 40 plus 0 plus 0 plus 0, proportional, new integral, accumulative integral, plus negative infinity because of derivative, which gives us negative 3.3. So again, because we had, come on, we got to start my fingers closer together. There we go. Okay, because we had a spike in the upward direction, derivative wanting not to have a ramp rate is going to spike it low. And so it spikes it as low as it can go, down to 3.3. That was position 19. And now 20 is back up to its set point. Now without calculating it, just thinking about it, we have no old integral, we have no new integral. It's an instantaneous spot right here, but we have plateaued, so the ramp rate is 0, so we have no derivative. No old integral, no new integral, no derivative. And there's no error, so we have no proportional. The only thing we have left is our bias. So for position 20, we literally go right back to 40. So we actually drop down to, oops. Okay, now get away. Leave me alone. Come on. So we literally come right back down to 40 and carry on because this doesn't move, so we carry on at 40. Okay? So literally what we have seen, now we're going to do this out quickly with a different color. Let's try this. Give me a different color now. Now that I want a different color, can you give me a different color? Come on. Come on. Okay. So now we're just going to do this out real quick with
Space color.
Rainbow.
Space color. There we go. Okay. Space color. Okay. So all I'm going to do is I'm just going to go over top of the line once again. Okay. So we came along. We went up on a ramp rate of 10% over the course of 10 seconds. We went 10 seconds at a steady state of 10% error. And then we went on a ramp rate down at 10% for 10 seconds and another 10% over 10 seconds. And then we did a plateau at minus 10%. And then we ramped back up at the same ramp rate. And then we had a square wave, so instantaneous. And it was 10% error and then a minus 10% error. Come back to our set point. Our output, starting at 40%, came over until we got a ramp rate. And as soon as we saw that ramp rate, it dived down due to derivative. Now, I do want you to be able to explain what is happening and why. Okay? So please keep that in your mind that that might be something you want to be able to do. There is a spike down due to derivative. Then there is, it continues on a downward trend due to derivative, proportional, and integral, all having an input on this one because it is ramping up. Because it's ramping, you have derivative. Because the error at spot 2 is minus 10, you have proportional. Because we have all this area to account for of error, you have integral, right? Then it spiked back up due to the fact that the ramp rate stopped. The derivative is, the proportional is still there, the integral is still there, but the derivative no longer has that ramp rate. Now, over the course of the next 10 seconds, you see our output trend down. There is no derivative because there's no ramp rate. There's no extra proportional, but we do have an accumulating integral, which we have to then account for. So that is why our output is saying, you still have positive error, you keep accumulating positive error, I'm going to keep giving you a little bit more negative of an output. Right? That makes sense. But now it starts to have a ramp rate, a negative ramp rate. Our derivative instantaneously says, whoa, I don't like ramp rates. So we have derivative instantaneously. Then over the course of the next 10 seconds, the ramp rate remains the same. However, we are still accumulating. We have already accumulated negative 0.66, negative 3.32, and now we need to accumulate another negative 1.66 of integral. At the same time, our proportional has went from 10 to 0. So now our proportional error is now 0. So instead of our proportional, actually, instead of having a negative output, has no output. We don't have any proportional output. But now, as it keeps coming down, it keeps ramping down, we come up at a steeper rate. Our output is outputting more because we are now getting our proportional back. Okay, but the proportional is going in a positive direction because we went negative 10. And our integral, it calculated out, okay, now I have a positive 1.66. But I have about a 6 point whatever, a negative 6 in my integral bank that I would have to then chip away at with this positive that now I'm going to start to do. And now that we get down to here, by the time we get to 0.8, our derivative stops because our ramp rate stopped. And so our derivative cuts out, and we don't have any more derivative. But that didn't affect our proportional. It didn't affect our integral. The only thing that changed from 0.7 to 0.8 was the derivative. And then as we go from 0.8 to 0.9, our proportional is not changing. Our derivative has no ramp rate, so therefore it hasn't come back. But yet we've gained due to our integral. So now we went from, I think it was 46 up to 48, or 45 up to 48, I think it was, due to the fact that all this accumulation of negative error now makes our controller want output a more positive number. Trying to make this come back, the process variable, to come back to the set point. That's what the integral is trying to do, is over time, bring your process variable back to the set point. Then we get another ramp rate, causing our derivative to make our output drop. Our integral didn't have any time. Our proportional did not change. The only thing that changed is we then got a ramp rate. Well, over the course of the next 10 seconds, our ramp rate remains the same, but our proportional goes from -10 to 0, error, and our integral is still accumulating more negative error. It accumulated all this negative error. Well, all that negative error matched all that negative error, so all that integral canceled out all that integral. But we still have the ramp rate, right? Or sorry, we still have this ramp rate, so we're ramping down. But then as soon as that ramp stops, we jump up because we no longer have a ramp rate. We no longer have, so we don't have derivative, we don't have any integral, new integral, or accumulated of old integral. And because we have a 0 error, we don't have any proportional. So we were left with the bias of 40, our starting point, which makes sense. Because our starting point, we started off at 50, and our set point was 50. We had no history before that for integral. Well, at this point, essentially, because all of our positive error matched all of our negative error, we have all of our errors canceled out. So now we have no history, right? We do have the history, but as far as the controller is concerned, we have no history. So now we're back at 40%. So then when we look at the spike, because of the derivative, we're going to spike down hard, as low as the controller can go. And then as soon as we hit the plateau, our derivative goes away. But we have decreased from 40 down to 30 due to the fact that now we have a positive 10% error. Now with that positive 10% error, we still don't have any, we no longer have derivative. We don't have any new integral. We don't have any old integral, but we have proportional. The proportional being a positive error, we have a negative proportional output. So we have 30. Then over the course of the next 10 seconds, it ramps down due to the fact of the positive error over time for the integral. So the new integral is now negative 3.32. So we went from 30 down to 26.68, right? As we had a step change due to the derivative, it spiked all the way up to 103. And then as soon as that ramp stopped and we got to here, it came back down. 2, we have a negative error, so we have a negative proportional error. We have a negative integral error. But this negative error is going to be positive output for the proportional. Because proportional, our direction is negative, so when we have a negative error, we have a proportional output. This is our output of the integral. So we have a negative integral output, we have a positive proportional output. So our proportional and our integral and our bias all put together give us something like 47%. Then over the course of the next 10 seconds, it was actually supposed to be 46.68%, right? Easy math. Then over the course of the next 10 seconds, we have to accumulate for that. We have to account for that accumulated error due to the integral. So it comes over to 50. It raises up that 3.3. We do a step change. That step change makes the derivative, makes it drop down, and then after it drops down and we no longer have the step change, our output comes back up to 40 because our integral matched our integral error positive matched our integral error negative, and so we had no integral left. We don't have any ramp rate, so we don't have any derivative. We don't have any error, so we don't have any proportional. The only thing we're left with is our bias. So all that equation we summed up in about 2 or 3 minutes right there on how it worked, how it actually operated without doing all the calculations, right? So now that we've seen it, we understand how the controller is supposed to operate. The next step is getting into not just how the controller operates, but how the controller is going to affect the system. Because now we have to start seeing the dead time between when the controller actually outputs to how the system is going to respond. And then we have to look at the time constant. How fast is the system going to respond? And so we have to start now turning our focus from the controller, from the inputting to what it's going to output, to what the controller inputting to the process system, to what it's going to receive back from the process system. And that's how we complete our loop to our output, to our feedback. So that's our PID control.